These nodes introduce capacitors and their most important properties and features. A capacitor consists of two metal plates separated by a dielectric with permittivity E, or actually epsilon. Here is one of the plates. Here is the other plate, and the red in between is the dielectric. The capacitance C is determined by the permittivity of that dielectric, the area of the plates, and it's inversely proportional to the distance between the plates. The symbol for a capacitor is shown over here. It's just two lines symbolizing the two metal plates of the capacitor. Current and voltage are usually shown together with the dependence on T, because the most important and most interesting applications of capacitors are for AC voltages, not DC voltages. The IV characteristic of a capacitor is I of t equal to C times dV of t dt. So the current is the derivative of the voltage multiplied by the capacitance of the capacitor. The capacitance is also equal to Q over V, which is charge over voltage, and it is measured in farad. And the dimensions of farad are amp seconds over volt if it's expressed in terms of this quotient of charge divided by voltage. Small capacitors are in the range from about 10 picofarad to several hundred nanofarad. A picofarad is 10 to the minus 12 farad, so that's a fairly small value. Larger capacitors are in the range from a few microfarad to some millifarad. A microfarad is 10 to the minus 6, and a millifarad is 10 to the minus 3 farad. And they usually come in the form of electrolytic capacitors, which use an electrolyte in liquid or paste form as dielectric. What's important to know is that electrolytic capacitors are polarized, and they will not work properly with the wrong polarization, and they can actually be destructed with the polarization being wrong. So when you build something with electrolytic capacitors, make sure you pay attention to the polarity of the capacitor. Because the current is the derivative of the voltage and the IV characteristic of the capacitor, it is such that if that voltage is a constant, then the derivative will be zero, and so no current will be flowing. And if no current flows, then the capacitor is an open circuit for DC, which is direct current. Okay, so if you connect the capacitor to a battery, after a while the capacitor will be charged, and then no current will flow anymore, and it acts like an open circuit. Capacitors can store and deliver energy similar to rechargeable batteries. The amount of energy stored in a capacitor with capacitance C is C over 2 times V squared of T. And V of T is the voltage across the capacitor at time T. Power, as we know, is the derivative or the rate at which energy is being delivered. So P of T is dWt dt. So using the chain rule on that formula for the energy, we obtain dW dt is equal to C over 2, and then the derivative of that V squared of T. So applying the chain rule, that's 2 times V of T times the derivative of V of T. So that's spelled out here. And if you rearrange that, it becomes C times dV of T dt times V of T. So this is the current through the capacitor. This is the voltage across the capacitor. So together, that is the product of current times voltage, which is the power. So that verifies the connection between that energy formula and the power in a capacitor. A capacitor stores energy in the form of an electric field between the two plates when they are carrying opposite charges. So here's a little picture positive charges on one side, negative charges on the other side. And then the green lines here are the lines of force in between those two charges. The force between two charges is given by this formula here, some proportionality constant k times the one of the charges, in this case the positive charge, times the negative charge divided by the distance in between squared. Okay, force times distance has units of Newton meter, which is equal to joules, and that is units of energy. So that's how the energy is stored in the capacitor. Two capacitors can be connected in parallel, just like we have seen that for resistors. If they're in parallel, the voltage across both of them must be the same. And the current splits up. The total current is I of t. It splits up into I1 of t and I2 of t. So we can write I of t is equal to I1 of t plus I2 of t. And using the formula for the IV characteristic for the capacitor, we get that this is C1 times dV of t plus C2 times dV of t, or combined together C1 plus C2 times dV of t dt. So the equivalent capacitance of two capacitors in parallel is Ceq equal to C1 plus C2. And that is slightly different than it is for resistors. For resistors, we found that two resistors in parallel actually give a resistance of R1 times R2 divided by R1 plus R2, whereas two resistors in series give us R1 plus R2. So that's basically the inverse of how it was for resistors. If you take two capacitors in series, C1 and C2, they both must carry the same current, and their voltages V1 of t and V2 of t, they add up to E of t. And we can compute then dV1 of t dt as being equal to 1 over C1 times I of t, and dV2 of t dt as 1 over C2 times I of t. And then we add those up to make it V of t, so we get dV of t dt is dV1 of t dt plus dV2 of t dt. That gives us 1 over C1 plus 1 over C2 times I of t. And if we multiply this out and bring it over a common denominator, then we get C1 plus C2 over C1 times C2 times I of t. The inverse of that is the equivalent capacitance. So equivalent capacitance is equal to C1 times C2 over C1 plus C2 for capacitors in series. Capacitors can be charged and discharged. Typically, you charge or discharge them through a resistor, which limits the current. And if that voltage source here, which we assume is a DC voltage source, if that has some positive or negative voltage, something non-zero, then current will flow through that resistor and the capacitor will be charged. Typically, we start out with a discharge capacitor, then Vc of 0 is equal to 0, and Vs, we make something non-zero, and then the capacitor gets charged up to whatever that voltage Vs is. If we set Vs equal to 0, which means we make a short circuit across that source here, and the capacitor is charged to some non-zero value, I chose B here, then the capacitor gets discharged. Here is the analysis of that scenario. We have a loop around here with a current I of t that flows through all of those elements. Vs is again a DC voltage. So the current is given by the IV characteristic of the capacitor, that's C times dVc of t dt, where we now call the voltage across the capacitor Vc of t. Vc of t plus Vr of t, the voltage across both those elements here, must be equal to Vs. So we can write that, well, first of all, we have to write what Vr of t is. If we know what I of t is, then Vr of t is equal to R times I of t, and that's equal to Rc times dVc of t dt, if we use the formula from up here. And then we can add up Vc of t and Vr of t to obtain Vs of t, so that's the formula down here. So now we have Vs of t is equal to Vc of t plus Rc times dVc of t dt for time greater than 0, with an initial condition Vc of 0, which is the initial voltage across the capacitor here. That's a differential equation, first order differential equation with constant coefficients. And what we would like to do is solve that for Vc of t. The actual method of solving is not something we want to do in this class, so we just write down the solution, which we have over here. Vc of t is equal to Vc of 0, that's the initial voltage across the capacitor, minus Vs, that is the voltage of the DC source, which we use to charge the capacitor, times e to the minus t over Rc plus Vs. So it's an exponential function here in time, decaying exponential function with the minus sign here. The decay rate is given by the time constant Rc of the circuit, which we obtain in combination of the resistor and the capacitor. Okay, we can check that this formula actually works by plugging it back into the differential equation that we had on the previous slide. The first derivative of this expression here is equal to minus 1 over Rc times that difference in voltages here times e to the minus t over Rc. The Vs here drops out. And then we can take Vc of t plus Rc times dVc of t dt. And what we find is that we have this component here, Vc of 0 minus Vs times e to the minus t over Rc. And that gets subtracted here from the derivative. And what remains is Vs. So that whole thing is equal to Vs, which is actually the differential equation that we had on the previous slide. Okay, let's look at two cases here, capacitor charge and then later capacitor discharge. If you want to charge the capacitor, then we assume, for simplicity here, that the initial voltage across the capacitor is 0, and the voltage source, the DC voltage source, has a value of A. Okay, plugging this into the solution of the differential equation, we find Vc of t is equal to A times 1 minus e to the minus t over Rc for times greater than 0. Okay, we use this Vc of 0 as our initial condition, so that's when our computation starts, and this result is valid for t greater than 0. If we plot that expression here, we get this red curve here, so that's the charge curve for that capacitor. It goes up here relatively steep in the beginning. In fact, the slope in the beginning is equal to 1 over Rc. You can see if you would take the derivative here, you would get 1 over Rc, and the two minuses here cancel. So we actually, if we know what the time constant Rc is, we can make a line here on the horizontal axis, then go up to the final value that we are going to get, which is A. And we make a straight line here, and the beginning of that charge curve follows that straight line, and then it kind of levels off. At time Rc, actually, we get, for this expression here, 1 minus e to the minus 1. That's approximately 0.632. So we're roughly 2/3 up after one time constant from this charge curve. The second case is capacitor discharge. So now we're setting the initial voltage across the capacitor to A, let's assume we have been doing a charge first and charging it up to A, and now we're discharging from that value A, and we set the voltage of the DC source equal to 0, which basically means we make a short circuit across that voltage source, and we're discharging the capacitor through the resistor. Now, plugging those values into the solution for the differential equation, we find that Vc of t is equal to A times e to the minus t over Rc, so that's an exponentially decaying curve. If you would take the derivative again, you get minus 1 over Rc times A, so that line here that goes from A down to Rc, that straight line, that's the tangent to the discharge curve at time 0. And at time t equal to Rc, we have A times e to the minus 1, which is approximately 0.368 times A. So we're roughly down to 1/3 of the original value after one time constant, and then keep going down from there. Another way how we can look at capacitor is in the connection of sinusoidal waveforms. A simple case is if the voltage across the capacitor is some VA, some amplitude, times cosine 2 pi ft. So f would be the frequency of that cosine, and VA is the amplitude of the cosine. Okay, then using the IV characteristic of the capacitor, we can compute I of t as being the derivative of this whole thing and multiplied by c. Okay, so the derivative gives us 2 pi f from here, so that goes in here. The derivative of a cosine is minus sine, so we get the minus sign here, the sine 2 pi ft. The VA stays, and the c comes from the IV characteristic of the capacitor. Okay, if we rewrite this in terms of cosine, then we can write this as 2 pi fc times VA, so that's the same thing as here, and then a cosine 2 pi ft plus 90 degrees. Okay, you can check, making a little drawing, for example, that minus the sine of 2 pi ft is actually the same thing as the cosine of 2 pi ft plus 90 degrees, so that's basically advanced by 90 degrees. What we find then is that V of t and I of t are related by 2 pi fc to each other for sinusoidal signals. Okay, so we have actually something that sort of resembles Ohm's law that we found for resistors. Basically, the voltage is equal to some proportionality constant like R times the current. Or in this particular case, actually, the current is equal to this proportionality constant times the voltage, with the exception that there is this 90-degree phase shift here. So that's something that we need to tackle here, that we cannot just drop that. We either have the sine over here, which is not quite compatible with the cosine, or we make both of those into cosines, but then we have to put in that 90-degree phase shift. So the way to actually solve that dilemma is by using complex numbers. And Euler's relation tells us how to get started on that. Euler's relation says that e to the j alpha, which is a complex exponential, is equal to cosine alpha plus j times sine alpha, where j is equal to the square root of minus 1. So e to the j alpha is a complex number with a real part of cosine alpha, it's this part here, and an imaginary part of sine alpha, that's this part here. Remember that for complex numbers, the j is not part of the real or imaginary part. The j just tells us where the imaginary part is, so only the sine alpha here is the imaginary part without the j. So using complex numbers, we can now write v of t, which we said was VA times cosine 2 pi ft, as being equal to the real part of VA times e to the j 2 pi ft. And I of t, which is c times dv of t dt, is c times this expression, but taking the derivative of that. So the derivative here is just a j2 pi f that comes out in front of the e to the j2 pi ft. So that's what we have down here. And then the c comes from the IV characteristic of the capacitor again. So we get I of t is the real part of j2 pi fc times VA times e to the j2 pi ft. E to the j2 pi ft is common to both v of t and I of t, so it appears both up here and down here. Okay, so dealing with that is actually redundant, because we know to begin with that both of them will have the e to the j2 pi ft in their expression. So what people do then is they actually drop that e to the j2 pi ft for most of the computation, and then they may bring it in at the very end when they have a final result. So what we're going to do now is we're going to concentrate on whatever is in front of that e to the j2 pi ft. So we suppress the e to the j2 pi ft, and we define two complex quantities that v with the underbar we say is equal to VA. That was the part that was in front of e to the j2 pi ft for the voltage across the capacitor. And I, that current with the underbar, which is equal to j times 2 pi fc times VA, and j again is of course the square root of -1. So this is the part that was in front of the e to the j2 pi ft in the expression for the capacitor current. Okay, and we're going to represent now the voltage and the current through those two complex numbers, this V underbar and the I underbar. And then we can actually write that, first we start from this expression here, I is equal to j2 pi fc times V, which you can verify with looking back to the previous slide. Or to put it into the form like Ohm's law, where V is equal to some quantity times I, we can write it as V equal to 1 over j2 pi fc times I. So this is essentially Ohm's law for capacitors when sinusoidal waveforms are used. Okay, this is not applicable to all kind of waveforms across capacitors. It's specific to sinusoidal waveforms. But sinusoidal waveforms are an important part of the analysis of electrical circuits. Okay, here in the sidebar you see that I and V are called phasors. That's the technical term for those. They only depend on the phase of the sinusoidal waveforms and not on the frequency, and that's of course the reason why they are called phasors. Okay, so now we can summarize here the Ohm's law for capacitors as being V equal to 1 over j2 pi fc times I, which is written as j times x times I, and the I here and the V are again phasors, and x through this definition here is equal to -1 over 2 pi fc. X is called the reactance of the capacitor, and it has units of ohms. So it is the equivalent of resistance for resistors, but it's a slightly different form of resistance for capacitors. It's resistance to sinusoidal waveforms as opposed to resistance to general voltage and current waveforms as we have it for resistors. Okay, we use this symbol, the symbolic notation here when we deal with phasors. So the I with the underbar and the V with the underbar. And the capacitor is now labeled as being J times X, which is equal to 1 over j2 pi fc, or equal to minus j times 1 over 2 pi fc. Okay, so what we find then is that for sinusoidal waveforms, capacitors act like frequency-dependent resistors. And that's a very interesting and useful property. It allows us to actually use capacitors to make such things that react either to high frequencies or low frequencies. We call them filters. So you can make a filter, for example, to play music with the bass frequencies enhanced, or with the high frequencies enhanced, or the middle frequencies enhanced, and thereby shape the waveform that you would like to listen to in an appropriate way using a combination of resistors and capacitors. The generalization of Ohm's law for phasors is V is equal to C times I. So V and I here are again phasors. C is a complex quantity and it is called impedance. Okay, impedance C is equal to R plus JX. So R is resistance, like we have seen those for regular resistors, and the units are ohms. X is that reactance, the resistance of a capacitor for sinusoidal waveforms. It also has units of ohms, but it's a complex number here altogether, that impedance with the units of ohms. And just to remind you, phasors can only be used with sinusoidal waveforms. They are not applicable to general waveforms like rectangular waveforms or triangular waveforms and so forth. We can, with this idea of impedance, we can actually now make more general expressions for resistance in quotes, like the combination, series combination of a resistor and a capacitor. And we can compute the equivalent impedance of that series RC circuit. So CEQ is equal to the impedance of the resistor plus the impedance of the capacitor, because they are in series and they have both the same current. And since the impedance of a resistor is just the resistance itself, it becomes R plus the reactance of the capacitor, which is 1 over J 2 pi fc. And that, if we put it over a common denominator, that gives us J 2 pi fcr plus 1 divided by J 2 pi fc. If you look at this formula, you see that for small f, this part here is small compared to the 1, so we just get 1 over J 2 pi fc. So that's just simply the impedance of the capacitor. So for small f, CEQ approaches the impedance of the capacitor, and this acts like a capacitor. For large f, the 1 drops out, and we can cancel the f and the c here, and actually the J 2 pi, and we are left with R. So for large f, CEQ is approaching CR, which is equal to R. So it acts like a resistor for large frequencies, okay, because then the capacitor acts like a short circuit. For low frequencies, the capacitor acts more like an open circuit, and so the capacitor then becomes the dominant element. We can do the same thing for R and C in parallel, which is this picture here. The equivalent impedance of the parallel RC circuit is computed just like we have been computing parallel resistors. CEQ is equal to 1 divided by 1 over CR plus 1 over CC. Okay, now we have the same voltage across both of those, but the current split up. So CR and CC are again the impedances of the resistor and the capacitor. If we bring this over a common, actually no, we don't do a common denominator here. What we want to do is put in for CR the resistance R, and for 1 over CC we put in the J 2 pi fc. So if we substitute the values for this impedance and this impedance, we get this expression here in the denominator, and then we multiply through by R, so we get an R in the numerator and 1 plus J 2 pi fcr in the denominator. In this case, for small f, this part here disappears and we have R over 1, so the equivalent impedance is just simply the resistor R. Okay, if we look back here, for DC, the capacitor is an open circuit, and all we have here is the pass through the resistor. For large frequencies, this F is large here, so it's large compared to the 1, so we get R divided by J 2 pi Fc R. So that is just 1 over J 2 pi Fc, which is the reactance of the capacitor, or the impedance of the capacitor, I should say. And so for large F, the equivalent capacitance approaches Cc, the impedance of the capacitor. And we can easily see that for large frequencies, the capacitor acts like a short circuit compared to the resistor, and so the current will flow through this branch here and not through the resistor.